Stars implode, planets grow cold. Catastrophe is the metabolism of the universe. I can fight monsters, I can't fight physics.
Hello Year 11, so this is the May 2024 walkthrough and also some predicts on what I think is going to come up on the 2025 paper just to help you with your last minute cramming. So let's look at the first question. So first question is a chapter 3 in the textbook, which is generating electricity. These are sort of waffly questions. Usually it's advantages, disadvantages, so you can see sort of here. It's asking for that, but let's look at the start of it. So you've got wind turbines may generate electricity when electricity is not needed. Two methods that can be used to store the energy from the turbines are heating water to a high temperature, pumping water uphill into a reservoir. So which energy store increases when the water is heated? So the key word there is heated, so that is thermal. So this is actually chapter 1, isn't it, in the textbook? So chapter 1 in the textbook is all to do with energy stores, energy transfers. So which energy store increases when it's pumped uphill? So which one is a reference to height? So usually height, we think mgh. So mgh is normally GPE. Okay, so that's a nice straightforward starter. So moving on to the next bit. Now usually with these sort of chapter 3 renewables, non-renewables, advantages, disadvantages, they usually ask you to compare some data because there's not really many formulas to use. Maybe there's efficiency, and that's about it really. So let's have a look at what we got. Now when you get tables like these and they say include calculations, the best thing I suggest you do is that you look column by column. So look at this column first, compare them, because it is a compare, advantage, disadvantages. Before you've even compared, just do some numerical comparisons, okay? And then we'll look at calculations also. So if you look at the first column here, so if we look, what I'll do, I'll split the page into A and B. Now you don't have to write paragraphs, it's not an English exam. So for A, it stores 33,600 kilojoules per 100 kilograms, and then if you look at B, that stores 490 kilojoules per 100 kilograms. Okay, so first thing I can do, I can say A stores more energy. Okay, so that's the first thing. So here's a comparison. So just compare column by column. Now look at the next one. So what can we see? A is 40% inefficient, or flip it the other way, it's 60% efficient. Okay, and then if you look at B, so B is 25% inefficient, okay, or it's 75% efficient. Okay, just take the obvious stuff first, and then we'll do some calculations in a minute. So if you look at the next bit, what can we look at? Installation. So A could be installed anywhere. Okay, so clearly that's a positive. B is restricted to maintenance location, so that's clearly not an advantage. Okay, so that I would probably say that's a negative. Now, all I've done so far is I've just compared. I haven't actually done any calculations yet, but now we could do some calculations. We can actually work out 40% of 3,360. So if you worked out, we can now work out energy wasted per 100 kilograms. Okay, so you just do 0.4 times 33,600. So that will give you, so we just get the calculator out. So that's 13,440 kilojoules. Okay, and then let's just do the energy wasted for the other one. So energy wasted. So here per 100 kilograms. So here you do 0.25 because we're trying to work out 25% of 490. So let's put that in the calculator. So that's 122.5 kilojoules. Okay, so once you've done that, yeah, I think we've got enough information there. We've compared the advantages, disadvantages, and we've also done our calculation. Again, expect that with these chapter 3 questions on generating electricity. This question is about wind turbines. Last year's 2023, their questions was on hydroelectric, and it was on I think it was solar panels. So usually they like to do comparing fossil fuels. So don't forget. So this is my sort of predicts. So what do I expect to come up? So if I just put down predictions, okay, for 2025. So I'm expecting for chapter 3, they haven't really talked about nuclear power stations, advantages, disadvantages. So look into nuclear power stations. Okay, so nuclear power stations, look at the advantages and disadvantages. Now, if they're asking you about advantages and disadvantages, maybe you need to look at the disadvantages of fossil fuels. Okay, so most of this revolves around burning of fuels. So burning of fuels releases carbon dioxide. Carbon dioxide causes global warming, climate change, or burning of fuels causes release of sulfur dioxide, nitrogen oxide, which causes acid rain. Okay, disadvantages, nuclear power station, obvious ones. It's to do with the radioactive waste, expensive to build, expensive to commission, expensive to decommission. Okay, advantages of nuclear power stations, they produce clean energy because there's no burning involved. Okay, in terms of what they could also do, they could ask about the national grid. Okay, so the national grid, as you know, you got the pylons and you've got the transmission cables, and then you've got your step up. Now, step up, they're not going to ask exactly what's going on inside that because that's actually chapter 15 or paper 2. But they could ask you about why do we transmit to high voltage. So here it would be high voltages. Okay, and we're talking up to about 400,000 volts. So why do we transmit to 400,000 volts? So obvious, this is a standard answer: high voltage, low current. So low current means low heating effect. So low heating effect, less energy loss. Okay, so it means it's more efficient. So it's really important you say it's efficient here. And then clearly we've got to step it down. So we need a step down transformer here. And why do we need to step it down or step down the voltage? Because 400,000 volts in your house will probably cause a fire. So you need to step it down to a safer voltage. Okay. Usually power stations produce it at 25,000 volts, which would be considered low voltage. Okay. So low voltage, high current, high heating effect, large energy loss, and inefficient. Okay. So that's what I'm predicting. Okay, so there seems to be more emphasis here on the renewables. Okay, so maybe there should be something about the non-renewables. So let's look at the rest of the question. This one, I've had a look at the mark scheme on this one. It's a bit, let's put it this way, it's not the sort of answers I'm looking for, or I would expect. So let's look at the questions. A decrease in the amount of CO2 released by different activities will help slow down climate change. Transport and generating electricity are the two activities that release the largest amounts of carbon dioxide in 2018. Explain one change that would reduce the amount of CO2 released by... so here, transport, obviously, we use cars. And what do cars do? They release CO2. Sorry, that's meant to be a small 2, by burning petrol or diesel. So what would you do instead? Use electric cars. Okay. Now they've got some silly answers here from when I had a look at the what suggestions. They're saying you could use public transport. Now, as when you're transporting electricity, I don't think you'll be transporting it on a bus. You certainly won't be walking or using your bicycle. But apparently those are legible answers. But I don't think anyone's brain is thinking that way. Okay, so generating electricity, obviously use less fossil fuels. Okay, that will get you 1 mark. So give an example anyway, like coal, oil, or gas, and then suggest what could you use instead. So use, and just name a renewable. So use solar, wind, etc. Okay, so any of those. So that will sort of your chapter 3. Now, other things they could ask in chapter 3. So chapter 3 was, as I said, it's the waffly stuff, advantages, disadvantages. Most of the, if you think about the renewables, okay, why do we go with renewables? Okay, so basically less CO2. Okay, the advantages of the non-renewables. Okay, so what are the advantages of non-renewables? When we say that, we mean the coal, oil, gas. It's cheap, readily available. Okay, so easy to dig up, and it's reliable. So reliable, what does that mean? Reliable means you can use it 24 hours a day. Okay, so, and that is, out of all the renewables, one of the biggest disadvantage of them is that they're not reliable. Solar you can't use when it's dark, obviously, and obviously winter months, less daylight hours. Wind if it's not windy. Waves, well, if there's no storms creating the waves, you've got no wave pair. Tides only come in twice a day. Hydroelectric is reliable, but there's a risk of flooding if you're constantly keeping it running 24 hours a day. Those are the 3 water ones. And then you've got geothermal, which is reliable. So you're sending cold water down to hot rocks. Hot rocks turns the cold water to steam. Steam rises, drives a generator. Drives the turbine, drives the generator, generates electricity. Problem with that, there's only very few locations where you've got these hot volcanic rocks. And then you've got biomass, which is burning living organisms, I guess, like leaves and so on, which sounds like they're giving off CO2. But don't forget, during their lifetime, they absorb lots of CO2. So therefore, they're carbon net zero. So they're considered a bit more friendlier. In terms of the nuclear, things to remember for nuclear, they're more energy dense. Okay, so they give off more energy per unit kilogram than coal, oil and gas. Okay, and certainly more than renewables. But obviously nuclear, you've got to look at the disadvantages. Expensive to decommission, expensive to build. You're looking at getting rid of radioactive waste, okay, burying it deep underground, containing steel vessels, handling with forceps, wearing radiation suits, and also what happens, risk of a catastrophe or a terrorist attack. Okay, so that's question 1. Okay, so just make sure you can. There's no sort of like writing too little, even though it looks like I've wrote very little here. But just try to focus on just advantages, disadvantages, and when you do give an advantage, disadvantage, try to explain why. All right, moving on to question 2. So this you might think is probably chapter 3 also in the textbook, nuclear power station, but it's actually part of it's actually chapter 7. Okay, so if you look here, process of nuclear fusion is used in nuclear power stations. Okay, so this is actually, if you look in the textbook, or if you actually follow the textbook, chapter 7, this is actually the last part of chapter 7. So this will lead us on to our predicts, what we hope or what might come up. So let's look at this question anyway. So fission, first of all, know your definitions. So let's do fission. So fission is the splitting of a heavy nuclei into two smaller nuclei, okay, plus energy. And I'll talk about this energy in a minute. Now, what is the other process is fusion. So fusion is the joining of two lighter nuclei into one heavy nuclei plus energy given off here also. Now, the thing to remember, let's do fusion first, because obviously this is not part of this, but it's something you should be thinking about anyway. Fusion is the fusion of two hydrogen isotopes, deuterium plus tritium, okay, to form helium. Now, if you look at the bottom numbers, they balance up. 1 plus 1 is 2. If you look at the top numbers, 2 plus 3 is 5, and you're left with 4. So there must be lots of missing mass. So what's happened to the missing mass? So the missing mass is what gets turned into energy. So the key thing here with both of these, with fission and fusion, the mass of the reactants is greater than the mass of the products. Okay, and the missing mass is what gets turned into energy. So what I'm trying to tell you here, what we're trying to tell you here, well, this is, so what happens in fission, you have uranium 235, 92, and that absorbs a thermal neutron, so a neutron at room temperature. Okay, and that's 10, and that becomes uranium 23692. So this is the unstable isotope. Uranium 235 is stable. We've made it unstable, and in the process, when it's unstable, it starts to sort of like rearrange itself, gets a bit unstable, starts changing shape, and then it splits. Now, you can split this into reactants and the products. So what do you get? The products, you get two daughter nuclei. Okay, so you got two daughter nuclei, you got 3 neutrons. These 3 neutrons may cause a chain reaction by finding other uranium 235. But the most important thing, the mass of the products is less than the mass of the reactants. So the missing mass gets turned into, so if the mass of the reactants is greater than the mass of the products, and the missing energy, also the missing mass gets converted to energy. Okay, so something to bear in mind. So now this is the stuff that should be coming straight to your head straight away. Okay, when you're thinking fission fusion, know your definitions and so on. So this will produce 2 daughter nuclei. Okay, it'll produce neutrons, and it will also produce the energy. Okay, and it's the energy we use to boil the water. The water turns to steam. Steam drives the turbine. Turbine drives the generator. Generator generates electricity. But don't worry about that yet, because that's obviously paper 2 stuff, or chapter 15. So let's have a look at what we're going to do here. So in nuclear power stations, energy is released from uranium nuclei. Okay, in this case, uranium 236. The uranium in figure 2 splits into 2 parts and releases 3 neutrons. So these neutrons, as we know, they can cause a chain reaction by finding other uranium 235. So it's interesting, they've talked about nuclear here in the radioactivity sense rather than the energy sense. Okay, so the process of nuclear fission releases electromagnetic radiation. So the only one here that's EM radiation is this one here, gamma rays, is in the form of gamma rays. Okay, or just write the word gamma rays. Okay, so that's nice and easy. They haven't asked about fusion. All right. So in terms of predicts, what do I think is going to come up, or what could they possibly test? Because they haven't tested it here, is conditions for fusion. So what do we know? Well, these two here are positively charged nuclei, so therefore they repel. Okay, electrostatic repulsion. So what do you need? You need high temperature and high pressure to overcome the electrostatic repulsion. So where do you get high temperature, high pressure? Stars. Okay, so how do they do how do they simulate high temperature? Clearly they're very hot. Okay, and how do they simulate high pressure? Huge gravitational pull. Okay, because they're large masses. So let's turn over. All right, so now is just use of formulas. So the first one, right, they do give you the formula sheet. Okay, so you're going to get it this here. So here's my version of the formula sheet, a bit chewed up. Okay, so write down the equation that links energy, power, time. So if you look here, power equals energy over time. Okay, so just write it down as is, and they'll accept it in symbol form, as they've already given you what the symbols mean. Okay, power equals energy over time, or energy equals power times time. Either or. All right, so nuclear power station has a power output of 500 megawatts. So that's your power, but the power is in the wrong units. Now, if you've forgotten your prefixes, I've made it here. So capital M, mega, means times 10 to the 6. Now, that means it's 500 times 10 to the 6 watts. Now, some of you are tempted, you're like, oh, mega, million, add 6 zeros. Yeah, that's fine. But you may as well just put, if you look at your calculator, if you just put 500 times 10 to the, and just put 6. Okay, just using the prefixes, that'll give it to you anyway. So there's no point you trying to count your number of zeros, especially if you don't know how to count zeros. Just put it into the calculator straight away. Okay, so calculate the energy. So they're asking for energy, question mark, and they've given here the time, and the time is in seconds, so that's great, and give your answer in joules. So this is nice and straightforward. So you get 1 mark for this bit here. Okay, so that's why it's 3 marks, because it's not really a 3-mark question, it's more of a 2-mark question. So calculate the energy. So energy is equal to power times time. Okay, so just put in 500 times 10 to the 6. Now, do I need to put all the zeros again? Don't bother, just leave it as that. Times 3,600. And then that will give you, so if I do on the calculator, so that gives me 1.8 times 10 to the 12 joules. Now, I always get in the habit of writing my units anyway, even though they give it. Sometimes you don't see it, and it's just worth getting the good habit of, not missing stuff out. Okay, so just keep this handy. You'll be surprised, how much you'll be looking at it. In fact, if you think about it, if you understand each formula, you've actually understood all the theory anyway. Right, so radioactive waste produced by nuclear power stations has a long half-life, so suggest one precaution taken to reduce the hazard caused by the waste. Okay, so what do you do to the waste? So, as we said before, you could bury the waste, okay, deep underground, and we're talking like 200-300 meters underground. Things like when you transport it in secure vessels in trucks, when you're taking it to these deep burial grounds. Okay, you could pour concrete over it, as will be the case if it's a catastrophe sort of scenario. And the other thing you can do, obviously, the uranium rods in nuclear fission. So here, if we go back, it's uranium, but you could also have plutonium. Okay, so just be mindful, they might ask what is another fuel. Okay, the uranium rods, once they're spent, once you can't use them in a power station anymore, they're still hot, for want of a better word. So what they do, they put them in what we call cooling ponds. Basically, it's like a recycling plant, and then this would heat up the water, and the hot water, you'd do something with it. Okay, so because they're radioactive for thousands of years, which brings us on to what our predicts will be in a minute. Okay, especially for chapter 7. Now, nuclear power stations do not generate electricity. So let's move on to the last bit, 2.5. This has got nothing to do with physics, just looks like a maths task. Okay, so one nuclear power station generated electricity for 92% of a year. 1 year is 365 days. Calculate the number of days during the year that the nuclear power station generated electricity. So basically just work out 92% of 365, or just do 0.92 times, 365. Now, again, I don't know what that's got to do with physics, but it is what it is. So 335.8. Okay, so that is this paper. In terms of predicts, what have they not asked? They've asked nothing about half-life. Okay, so half-life calculations, make sure you can do those. Okay, nothing about uses of alpha, beta, gamma. Okay, so when I talk about that, what I mean is, if I gave you an example, we need a radioactive tracer to test how well someone's intestines are working and so on. What would you give them? Well, if you're trying to see, you basically make them eat food and make sure the food's radioactive. What radiation would you use in order to be able to detect it from the outside? We're going to have something that passes through your skin. So, you wouldn't use alpha because you wouldn't pass out. And you certainly wouldn't use alpha because it's highly ionizing and it's going to kill you from the inside. So it's going to damage your cells, mutate your cells, cause cancer. Okay, so you need something that will pass through easily, so beta or gamma. But then you need something that's not going to ionize as much as it comes out, so you use gamma. So think about the appropriate alpha, beta, gamma in terms of penetrating ability. Okay, and then think in terms of half-life. So if you're tracing food through your digestive system, well, the whole procedure is going to take about 2 hours. So you don't want a half-life of 2 minutes or 10 minutes. You want a half-life of a couple of hours, but you don't want a half-life of a whole day, because a whole day means you're going to be ill for the rest of the day when you're at home. Okay, another example, looking for leaks in water pipes under roads. You'd contaminate the water with gamma. Why? Because gamma can pass through the tarmac and so on, and the layers of rocks and whatever. So you can detect it from above, so you don't have to dig up the whole city. Now you have to think about what sort of half-life would you need now? Well, in terms of half-life, you would need probably a longer half-life, because you're going to have to detect it through probably half the city. So you were talking about hours. Would you do days? No, because people need their water supply. Okay, so it's sort of like thinking about it socially, ethically, morally sort of thing. In terms of half-life calculations, make sure you just remember to keep halving. Okay, and loads of examples you see in past paper questions. One thing they haven't done for a while is decay chains. So if they said, for example, I'll use uranium-235 because that's the most common one. Okay, now goes through 4 alphas and 2 beta decays. So what does that mean? Well, alpha is 4,2, isn't it? And beta is 0 minus 1. So 4 alphas means top number 16, you subtract 16. So 235 minus 16. So 235. So 219 uranium, and then bottom number, if it's 4 alphas, you minus 8. Okay, so you're left with 84 after 4 alphas. Now, once you've done 4 alphas, now there's 2 betas. What would betas do? Nothing to the top number, so 219. Let's call that X, sorry. Let's call that Y. And the bottom number, minus 1. So 2 minus 1s. So therefore, the new substance is going to be adding 2. So that will be 86. So alpha decay chains or beta decay chains, gamma obviously doesn't do anything to it. The other thing that has not come up, okay, on this one, and can't remember, has it come up in 2023? It may have. So what you want to look at is the Rutherford scattering experiments. Okay, so make sure that's something for you to look into. Okay, Rutherford scattering experiments, shooting alpha particles at a thin piece of gold. Okay, what did you expect? He expected all the alpha particles to pass through. 99% of them pass through. Okay, some deflected small angles. Then 1 in about 10,000 backscattered, which didn't make sense. Okay, because obviously the model at the time was that all the positive charges, the protons were spread out. Okay, so there's no way they could repel something with a charge of +2 because that's what alpha has. So obviously people had to change what they thought the nucleus looked like or the atom looked like, and then realize all the positive charges must be in the center. So that could be more positively charged or densely charged enough to be able to repel an alpha particle. So then came the nuclear model. Okay, so just make sure that has not been tested. Okay, so that's something to look into. Okay, so that is your question 2. All right, question 3. So this is the one of the required practicals on this paper. So there's 5 required practicals they could probably ask you to do. I'm going to come to that in a minute for my predicts. So first of all, this one's still investigated how the length of the wire. So that's one of your variables, affects the resistance of the wire. Now resistance, hopefully straight away you should realise resistance is equal to V over I. So we know that because it's on your formula sheet over here. So they call it V equals IR. Okay, so in terms of what you need to measure, so length, clearly you need a meter ruler. So whenever you see a quantity, make sure you can state a piece of apparatus to measure that quantity. So V voltage, voltmeter, I current, ammeter. So the student plotted a graph of resistance against the length of the wire. So you may remember doing this. You probably remember burning it. Okay, so why did you burn it? Because when the wire, the crocodile clip was really close to each other, the length of the wire was really small. And what do you know about resistance and length? Resistance is proportional to length. Okay, and the other thing you should have learned during this topic, resistance is inversely proportional to area. Now I'll come back to that in a minute because it's not something they test often. Okay, so it's not something you should probably overly concern yourself with, but I'll go through a couple of examples of what they could possibly do. So describe a method. So this is your 6 marker. We'll have a bit of a discussion about what 6 markers will be. So describe a method student could have used to collect the data needed to plot the graph. So you're going to, if it's a graph of resistance against length, if you just look at these here, you're varying the length and you're plotting the resistance. Okay, so start off with that. So start off by saying start at. Now think of a nominal length. Now, if I was you, I would say start higher. So start at 100 centimeters. Okay, so when it's 100 centimeters, so put the crocodile clip at 100. Obviously switch it on. Switch circuit on. Okay, and then what do? You're going to measure the voltage and the current. So this is what you measure. So measure the voltage using the voltmeter and current using the ammeter. Okay, and then once you've measured those, then you're going to calculate the resistance. Okay, so calculate resistance using V over I. So you must state the formula because this is a method. Whole point of a method, logical, sequential. Someone's got to be able to follow it. Okay. Once you've done that, move on to, so repeat for 90 centimeters up to, let's say 50 centimeters in 10 centimeter intervals. Okay, so that's what you got to do. And for each one of those, just measure V, measure I. Okay, so in terms of why have they got the resistor here? Why have they got a switch? Okay, what does current do to anything? Current causes things to heat up. So you do not want the temperature to increase. These two only work if temperature is constant. Okay, we'll come back to that because that is actually what Ohm's law states. All right, so now repeat for night. So what do? Switch off when not in use. And for accuracy, obviously, you've got to repeat readings and so on. But when you repeat readings, make sure you keep the temperature low. You do not want to use lower values of L. like 40 centimeters, 30, 20, because what that would do, that would reduce the resistance. So the smaller the length of the wire, the smaller the resistance, the bigger the current. Because resistance, if you look here, is inversely proportional to current. So whenever you talk about current in a question, talk about resistance in the same breath. Current goes up, resistance goes down. Current goes down, resistance goes up, or vice versa. Whenever you're talking about resistance, talk about current. Okay, and then you just what you have to do? Plot a graph of resistance on the y-axis against length on the x-axis. Okay, so if you look at that method, could you follow it? Yes. Could you collect enough data? Yes. Okay, so it's logical, sequential, haven't missed anything, nothing fundamental. Okay, talked a bit about safety aspects, talked a bit about accuracy, about repeat and so on, so that's great. Okay, now moving on to this thing here. So as I said, in terms of theory, all you was told, I'll just put it here, you were told about Ohm's law. And you were told, well, Ohm's law, straight away, you think IV graphs, and it looks like that. So something that is ohmic follows that. That means current is proportional to voltage. Now, current will only be proportional to voltage so long as temperature remains constant. So long as temperature and other physical factors remain constant. Okay, so what are the other physical factors? We've sort of talked about them here. Length. The longer the piece of wire, the more atoms in the way, the more collisions with the electrons, the more resistance, the more energy the electrons lose to thermal energy, the slower the electrons, the smaller the currents, the bigger the resistance. Resistance is inversely proportional to area, or the thickness of the wire. So think of a tunnel. The wider the tunnel, even though the length of the tunnel is the same, the more space is for you to go sideways and avoid collisions. Okay, so the wider the tunnel for the same length, the less resistance there is. And so if I give you an example, so obviously from this here, we know this is the correct answer. So if you've got, let's say, for example, L, and cross-sectional area A, and I said to you that was 10 ohms, and then I said to you, well, there you've got 2L and A, well, what would that be? Well, you double the length, so that's 20 ohms. Okay, now if you started off with L again, okay, as A, and let's say it's 100 ohms this time. Okay, this time I've kept L the same, and now I've made it 2A. Okay, so now if you look here, it's inversely proportional. So if you double the cross-sectional area, you halve the resistance, so it becomes 50 ohms. So if you halve the resistance, you've increased the current. Okay, so just again, when you talk about resistance, try to talk about current. So let's say, for example, we had L and A, and that gave 100 ohms. Now, what would happen if I said to you, well, what is 3L and 4A? So 3L, that means you triple it, so it becomes 300. And 4A, that means you divide by 4. So it's just 300 divided by 4. So that becomes 75 ohms. Now, how could they make that more difficult? They won't give you the area, they might give you the radius or the diameter. So just remember, area is pi r squared, or pi d over 2 squared. So if I said to you now, so let's say we're using this one here. If I said to you 3L and 3R. Now 3R means R. Now don't forget, because it's R, you've got to square it. So that means 9A. Okay, so what does 3R do? 3R makes it 300. 3R, you got to divide by 9. So you just got to do 300 divided by 9. So that gives you 33.3 ohms. So just be mindful of things like that. What they have not asked, and I'll come back to this in a minute. So let's just finish this off. and then we'll do our predicts in terms of required practicals. Okay, a student used a cell that had a potential difference of 1.5 volts. Explain why the cell was not an electrical hazard. Well, such a low voltage would not cause an electric shock. Okay, you certainly won't be electrocuted off it because you're not going to die of 1.5 volts. Okay, so now it's a bit early because we haven't looked at the other practical, but just let's have a sort of gander at the last 3 years. So for the 2024 paper, they've done a 6 marker on resistance against length. Okay, the other practical we'll look at in a minute is going to be the density one. Okay, so that's what's happened in 2024. Very unlikely they're going to do these 2 again this year. Okay, because they've got to test all 5 practicals over the course of at least 2-3 years. 2023, they did specific heat capacity, and the 6 marker was on the IV graphs. So I'm not expecting a 6 marker on the IV graphs. Okay, I am expecting a question about the IV graphs. So you need to be able to memorize and explain the IV graph for a fixed resistor, ohmic, straight line, okay, fixed resistance, constant temperature, and then draw the shape and explain the shape of a filament bulb, which is a classic question I love to ask. As voltage increases, current increases. As voltage increases further, the bulb gets hotter because obviously it gets brighter. The atoms in the filament vibrate with greater amplitude, increased collisions with electrons. Electrons lose more energy, the current decreases, the resistance increases. Okay, so make sure, for example, if that was the IV graph for the fixed resistor, which we know is ohmic, i.e. straight line going through the origin, make sure you can explain what I've just said. So it should, if you did the IV graph, there are IV graphs on the AQA spec, not VI graphs. It should look like this. If it followed the fixed resistor, it should be like this. But as you can see, the current decreases because the resistance increases because of the heating effect. Okay, that's why this is not ohmic, because for current to be proportional to voltage, temperature must remain constant. Okay, so, and then the other one, now they can ask you to draw the shape. What else could they do for the diode? So the diode, as you know, only allows current to go in one direction. The direction is this way. Okay, so follow the triangle. If it comes this way, it hits the brick wall, infinite resistance. So what do you know here? I equals 0. So what do you know about the resistance? Resistance is infinite. Here, I is increasing. So what do you know? Remember I said if you're going to talk about current, talk about resistance. So resistance is decreasing. Okay, and here, current is increasing rapidly, therefore resistance is decreasing rapidly, almost to 0 because it's very steep. Make sure you can describe those. This one, explanation in terms of particle theory, explanation in terms of lattice ion or the atom vibrations and electron collisions. Okay, so hotter it gets, bigger vibrations of the lattice ions, more collisions, more energy lost by the electrons, so it gets hotter, the filament gets hotter, electrons lose more energy, they're moving slowly, therefore they have got a low current. Low current means high resistance, so that's why it levels off. Okay, so I'm not expecting IV graphs to come up as a method, I'm expecting it to come up as an explanation. Okay, and you've got to do some, obviously you've got to do some calculations. R is V over I. Okay, so just remember that. Now, what else came up? Specific heat capacity came up, but it was about variables. What would you change? Would you keep the same? Results and graphs, analyze a temperature time graph and so on. So if you've done the paper, you'd have seen it. And if you go as far back as 2022, what did you notice? Thermal insulation. Okay, so that hasn't been tested for 2 years now. Thermal insulation, and certainly not as a 6 marker. However, it's a very simple 6 marker to explain. Thermal insulation, put hot water in a beaker, change the number of layers of one type of insulation, and measure the temperature drop for different levels or layers of insulation. Or same beaker, different types of insulation of the same thickness and measure the temperature drop over a certain time and draw your cooling curves. Okay, and just what can they do? They can give you the graphs and they can ask you to analyze it. Would they ask you to do a plan of that? It seems a bit, I don't know, it's something that I don't think, I think most likely they haven't asked the 6 marker for specific capacity. Density comes up a lot, so I think they've killed that one for a while. They've done a 6 marker in 2022 whether you had to write a plan for regular solids, so density is mass over volume. How do you work out the volume of a regular solid? Just use a formula. If it's a cube, length times the base times width. If it's an irregular solid like a brick or a stone or even a little toy, I guess, displacement method to work out the volume. Okay, so that has come up. Very simple. Would it come up again on a higher paper? I'm expecting something with a bit more difficulty. So I'm expecting probably specific capacity. I certainly wouldn't be focusing on resistance against length or density gain. Maybe they can ask density formula, which we'll look at in a minute. Now, series and parallel is a tricky one because that is not really a very big experiment. Now, if you didn't remember the experiment itself, in series, what do they ask? They ask, could you work out the current and voltage, okay, of 1, and then could you work out the current and voltage of 2? And well, I guess you don't really need the voltmeter here. So they're going to ask you, how does the current change? Increasing the number of resistors causes, if you look at this formula, if you increase the resistance, the current will drop. Okay, and then they could ask for parallel. So what they'll do, hopefully they'll give you the pictures. They're not. I'll be surprised if they ask you to draw these. Okay, so they'll give you one. Okay, measure the voltage across it, and then they'll give you, so that will look exactly like that one, and then they'll give you two. Now you may remember doing this, although you may not. It wasn't the most memorable. And then they'll say, well, now you've got 2. Now this is not the current going through any of this. This is the total current, because at this point here, or at this point here, sorry, I1, I2, current split. So I is equal to I1 plus I2. But here, as you have more resistors in parallel, as you add more and more and more, then the total current increases. As you add more resistors in series, like 3 and 4 and 5, the total current decreases. Okay, now will they ask you that as a required practical? I seriously doubt it. Okay, it might be some calculations, it might be an explanation, just like I've just done here. When you put things in parallel, the total current increases. When you put things in series, the total current decreases. Because the total in series, especially RT is equal to R1 plus R2 plus so on. Okay, you do not need to know the formula for the total resistance in parallel. Okay, that's an A-level formula. Okay, so this is my sort of predicts. Take from this what you will. Okay, they haven't done thermal insulation for a while. Series and parallel, I'm not looking for that to be honest. Density has been killed. IV graphs, maybe they can, but will they do it as a method? I'll be surprised. They haven't done a method for specific capacity for a while. Okay, so that's something to look into. So make sure you go back over the specific capacity, look over some past papers, watch some videos, make sure you can write a method, look at some past paper mark schemes for it. If you're in my classes, go into the classroom, find the specific capacity exam pack, practical exam pack that I gave. If you're not sure, just email me, I'll email you back, and look at how they write a method. Okay, stick to what they do. All right, so that's something to focus on. So let's, again, like I said, we still haven't done the other practical, which is density, which I'll look at in a minute. Okay, on to question 4. So question 4, this looks like static electricity. Okay, so I guess that's chapter 4 if you follow in the textbook. So what we got here, the rubber belt is turned. So this is your Van de Graaff generator. Rubber belt is turned by a motor. Okay, so the motor's at the bottom here, so that's causing this to go up and down. As the rubber belt moves, charge is Q. So whenever I think Q, there's 2 formulas you can use. Q equals IT, which hasn't been used, so look out for that one. And you've also got if you look at your formula sheet, so this formula sheet obviously given, you've got Q equals IT and you've got E equals QV. So it's these things should be part of, for want of a better word, these things should be flowing just like charge to the front of your brain. Okay, so what happens as the rubber belt moves, charge is transferred from the rubber belt, because this is rubbing against something inside, to the dome. So this dome is now negatively charged. So what we say, if there's a buildup of charge, and this is really important because I'm going to sort of predict what they could possibly ask. If there's a buildup of charge, we call that a high potential difference. Okay, so the reason why I say that, so think of like, why do you ever get a spark? Okay, so why, when you touch the, especially in Saudi where it's very dry and a bit arid, okay, building up charge happens quite frequently. So you get a bit of a spark when you touch like the railing, metal door handle, or when you touch the tap, water tap, and so on. So why did that occur in the first place? Now, I'm not going to answer the question yet. The question is actually reasonably straightforward. In fact, by drawing up the information you know in the first place will help answer it. So two insulators rub together. So think about, let's say you're walking on your carpet, your socks and the carpet are two insulators. So there's electrons are transferred from one to the other. Electrons are negatively charged. Only electrons are allowed to transfer. Protons, positive charges, stay inside the nucleus. We're not talking about anything happening in the nucleus. That's nuclear physics or radioactivity. We're only ever talking about the orbiting electrons. So by rubbing, you're forcing electrons to be rubbed off one and onto the other. So one of them becomes negatively charged. So let's say, for example, I'm walking on the carpet. My socks are rubbing the electrons off by friction. So my socks become negatively charged. So those negative charges, and they're built up on me. And because they're all the like charges, they want to repel each other. So when you probably notice when some people put their hands on this, their hair stick up on end because the electrons are going to their extremities and they're trying to repel and get away from each other. And in the process, what they're doing, they're causing your hairs to move up and out. Okay, high potential difference. Okay, and if you bring a conductor nearby, so basically you put your hand near a tap or something metal, bring conductor nearby. If there's enough potential difference, okay, it will break through the insulator, which is air, break through air, which is an insulator, and the charge flows. And the charge is basically the electrons, okay? And we call that a current. And what formula could we use? I is Q over T. Okay, so that's the link. Okay, so that's sort of things you should be sort of focusing on. Okay, right. So let's have a look at the question. What's this about? Right. So here we go. So figure 5 shows a student touching the metal dome of the static electricity generator. The dome is negatively charged, as we said. So if this is negatively charged, now every bit of these negative charges have found a path to go to, not quite to Earth, because she's probably standing on a polystyrene box. If she wasn't standing on a polystyrene box, she'd probably get a shock, as you've all experienced before. So why do the electrons here stand on end? So the electrons are transferred to the student. Okay, and these are all, as I said before, negatively charged. Okay, so they repel. So like charges repel. Now, as I said, what they haven't asked about static electricity is dangers. So this thing here, all right? So this is, now this we've talked about, like you get a spark off a metal tap. This is exactly what's happening in lightning. So where's the build-up of charge? Two clouds rub against each other. Okay, so when the two clouds rub against each other, builds up a high potential difference. Okay, build up a charge on the bottom level. So all the negative electrons build on the bottom level of the clouds. So huge potential difference between that and the Earth, which is at 0 volts. If enough potential difference, then the electrons will break through the air, which is the insulation layer, and cause a discharge of electrons. Okay, so just think of And that could be anything. Okay, so just think like classic examples are given. They always talk about fueling a car. So you got the fuel going through the rubber pipes, so build-up of charge. Okay, so high potential difference. You bring it near a conductor, i.e., the nozzle or the fillet, the what do you call it, the tank cap, causes a spark. Something flammable nearby causes a fire. Okay, which is not pleasant. All right. Okay, so just be mindful what they could ask in terms of that. Anything else with static, they could probably then ask, well, how do you protect yourself from a build-up of charge? So you need an earth wire. So an earth wire is basically a conduction wire, and all the conduction wire does, every time there's a build-up of charge, you would connect her to earth, and these electrons would flow down. So there will be no build-up of charge and the hair will go down. So there's no high potential difference, there's no chance of a spark. Okay, so that's what they call conduction lines, or sometimes they're called bond lines, or sometimes they're called earth wires. Right, so the next bit here, charged metal dome creates an electric field. So two types of fields you need to know about. So positive field around a positive charge and a field around a negative charge. Okay, so this one is in and this one is out. So what I'm going to do, well, let's answer the question. Well, what is a field? The field is anywhere where something experiences a force. So in an electric field, what experiences a force? An electric charge, whether it's positive or negative. Look at the other two examples of fields that you're going to come across. In a magnetic field, a magnet or a magnetic north experiences a force. In a gravitational field, a mass experiences a force. So what is electric field? It's basically a region where a charged object experiences a force. Now, for electric and magnetic fields, those will be attraction and repulsion. For gravitational fields, it will only ever be attractive. Okay, so and again, this question that I'm not sure whether some of you might ask, well, why is the lines outwards for positive, why are the lines inwards for negative? And you could even ask the same question for magnets, but obviously we'll talk about it some other time. This is the direction of the force experienced by a test positive charge. So if you bring a test positive charge towards it, it will repel it. If you bring a test positive charge towards a negative, it will be attracted towards it. Okay. Now you can probably apply that to magnetic fields. Why does it come out to the north and into the south? Because when you place the test magnetic north near the north pole, it repels, so the arrows go out to the north pole. And if you put that test magnetic north near the south pole, it will go in towards get attracted, go towards the south pole. Now, how does the electric field strength vary as the distance from the charged metal dome increases? Hopefully you realise whether it's magnetic field, gravitational field, or electric field. If distance increases, then the field strength decreases. So hopefully that's obvious. Okay, so now let's moving on. So now you've got some, like I said, here we go. So you've got a spark transfers this much energy and this much charge. So that's your coulombs. Okay, however, as we said before, I've lost my formula sheet. Here we go. Okay, so if we look here again, well, you got micros times 10 to the minus 6. So it's 2 times 10 to the minus 6. Again, do you need to worry about counting the zeros? No, you just put that directly in. Transferred from the dome to the earth conductor. Okay, so why did it transfer? Large potential difference, and eventually such a large potential difference, such huge amounts of repulsion between the electrons, such that they were able to break through the air as an insulator to the earth conductor, and therefore this will then take it to earth. Okay, if you're in the way of that, obviously you now become part of the circuit, hence you get a shock. So calculate the potential difference. Potential difference, PD, is another word for voltage. So what formula connects E, Q, and V? Okay, so what we got here, if you look, E, Q, and V, energy transferred, charge, and potential difference. So E is equal to Q V. Now there's 1 mark already because this doesn't seem like a 3 marker. In fact, it doesn't even seem like a 2 marker, but obviously there's a unit conversion. Okay, first thing to do, put your numbers in, get your marks for substitution. As much as you might think your math skills are really hot, okay, you don't want to lose marks for that. So there's 1 mark, 2 mark. You're not going to get marked for the formula anymore because it's given. Okay, so you got 2 marks and you haven't even done anything yet. Okay, and then rearrange. So because they're multiplying, if you want to get this over to the other side to get V on its own, you've got to divide. So 0.6 over 2 times 10 to the minus 6 is equal to V. So it's obviously going to be a big number. So V is equal to 300,000 volts. So just put the answer there, or just leave it there. They should be able to mark it anyway. Okay, now let's look at the next bit. Which of the following changes would increase the distance a spark can jump between the dome and the earth wire? So basically, how can you get a bigger lightning bolt? So think of the clouds. Why did the clouds have a bigger lightning bolt? Because huge amounts of charge was built up. Huge amounts. We're talking, you know, compared to this, probably a scale factor 1 million, maybe more, because the clouds are huge, right? Okay. So, and what do they have to pass through? They have to pass through the air as an insulator. So the better the insulator, the harder it is for them to break through. Okay, so think carefully. If you decrease the charge, that means low PD. Low PD means small spark. Okay, you're not going to get a big spark. If you decrease the electric field strength, what causes the field is the dome. If you decrease that, then you're going to get a low PD. No good. We want a increase, so we want a large PD if possible. Okay, large potential difference. Think of the clouds. Decrease the electrical resistance of the air. That might be it, because what has to flow, remember what we said? Current flows through, doesn't it? This is charge, okay, which is equal to IT. So decrease the electrical resistance means increase current. So that could possibly be, let's just check, decrease PD. Well, that's clearly not what we wanted, is it? We want a large PD. So that's static electricity. Again, what did they not put on static electricity? Will this come up? That's quite a large question on static electricity. And they normally never do this much. Okay, maybe they could ask about dangers. So when we're talking about dangers, we're talking about this thing here: build-up of charge, high PD, bring conductor nearby, break through the air as an insulator, charge flows current. Use a conduction wire or an earth wire to prevent the build-up of charge, and therefore stop any sort of spark. So therefore you want materials with a low resistance. Okay, that's what conductors are, aren't they? They have low resistance. Okay. Okay, moving on to question 5. Now, I didn't do a predict on question 4, really, but question 4 is actually part of question 5, because question 4 and 5 is actually chapters 4 and 5 put together. Okay, so this is chapter 5 of the textbook, if you're following the textbook, which is mains electricity. So figure shows a student putting a coin into a vending machine that sells food. Vending machine is connected to a mains electrical supply. What's the frequency in PD of mains supply in the UK? So it's 50 hertz and 230 volts. Okay, just be mindful if you're doing this in Saudi's 220, but you've got to put 230 because UK. Now, in terms of what else do we need to know for mains electricity? So you need to be aware of 3-pin plug. Okay, that was chapter 5, and also fuses, electrical safety, and so on and so on and so on. All right. So in terms of this question, so just be mindful here. When they talk about mains electricity, don't forget you need to know about the 3-pin plug, okay, and also the 3 wires. Okay, so you've got the live wire, which is at 230 volts, and that is the brown one. Okay, you've got the neutral wire, which is at 0 volts, and that's the blue one. And then I'm going to put striped, it's normally yellow and green. And that is the earth wire. So what does that do? That basically carries excess current back to earth. Okay, now what other features do we have in a plug? You've got the fuse. So the fuse, if you remember, I think there might be a question about this later on, has the line down the middle, basically a weaker wire or weak points. Too much current passes through, that melts, breaks the circuit. What's the problem with a fuse? Slow responding. Okay, it takes a while for the current to heat and melt it. In that time, that extra current could have gone and damaged your circuit, and obviously you need to replace it. So what do we have instead? Okay, instead of a fuse, what do houses have? They have RCB, or circuit breakers, or fuse boxes as you call them. What do you know about these? As soon as there's a surge in current, the switch flicks down. Okay, so they're fast responding. And do you need to buy a new one? No, you just need to switch back on. Okay, so they're much better. Okay, in fact, your house would probably be condemned if you haven't got a fuse box in there. Okay. Right. Vending machine identifies the value of the coin by measuring the resistance of the coin. The power dissipated, so the power is equal to 340. Now remember what we said? We've got milli, so milli is times 10 to the minus 3. Okay, and the current I is 0.75. Okay, so what do we know? And let's just calculate the resistance, question mark. Okay, so now we've got to look at our formula sheet. Well, when you think power, most people think power equals IV, which is fine. So, and then when you think resistance, as we said, resistance, you think V equals IR, or R equals V over I. But don't forget, there's many versions of power. So power obviously is energy over time. Then you've got power equals IV, you've got power equals I squared R. So use this one if you don't know V. Use power equals IV if you don't know R. Then the other one you've got, I don't think you're given this one, power equals V squared over R. So probably you won't be expected to use that. But look here, I've been given P, I've been given I, I've got to work out R. So most likely I'm going to use this one. Okay, so P equals I squared R. So again, put your numbers in first. So 340 times 10 to the minus 3 is equal to 0.75 squared times R. You can work that out if you want first, but I'm just going to leave it as it is. So R is 340 times 10 to the minus 3. And again, if you want to put that into decimal, it's up to you. But there's no point me making a mistake here, is there? So I may as well just keep it as it is, 0.75 squared. So you put that in the calculator. Okay, and then the answer is 0.60 ohms. Now, you're probably thinking, why did I put the 0 at the end? Because I could have left it as 0.6. This is 3 significant figures. This is 2 significant figures. So I should give it to 2 or 3. Okay, so at the minimum. Don't give it to 1, because they'll ask you, why have you lost the data? Where's that extra significant figure gone? Well, clearly we haven't lost it. You're just going to be bothered to write it. Okay. 5.3, coins that are dirty are not recognised by the vending machine. Don't forget, the vending machine works on measuring resistance, which is V and I. So R equals V over I. So it measures the resistance. So in order to measure the resistance, it's got to know the voltage, it's got to know the current. So if it's got the same resistance, the same coin, it must have the same current going through it. Coins that are dirty are not recognised. So dirt is an insulator. Okay, so state the obvious things first. So if it's an insulator, what do we know? It changes the amount of current. So compared to a clean coin with no dirt on it. Okay, so at least if you're not sure what to write that down. Now, if you're thinking, what on earth is this? I've never seen a vending machine before, or certainly never put a coin in there or looked inside it. Who cares? Changes the amount of current, therefore alters the resistance. Okay, so that is there. So again, nothing to worry about here. So here we got what we call potential divider circuit. And don't worry if you haven't heard of that before. You don't need to know it. So this is essentially a series circuit. Now, what do you know about series? Voltage is shared. So that means if you put a voltmeter here, I'll call that V400. And that's obviously V. So 12 volts is equal to V400 plus V. Voltage is shared. So the voltage of the power supply is equal to the PDs, or the voltages across the two components, because that's a sharing. And then what do we know? Current is the same. So the current going through the circuit is the same at every point. All right. So the circuit symbol for a thermostat has not been included, so just draw it. So just draw a resistor, the one with the crooked line. Now, which way does it go? Someone asked me before. Doesn't really matter, so long as it shows somewhere where it's crooked. Okay, so what's the other way? It's probably that way. Again, just show something crooked. It's fine. It's not this one. Some people seem to confuse. That there is a variable resistor. Job of the variable resistor is to alter the current. And why do we need to alter the current? To control the temperature. Okay, because what does current do to wires? Causes it to heat. Excessive heating causes excessive resistance, which we don't want. And plus, it'll burn it anyway. And it might give you a shock, so you don't want that either. Right, so what do we know about this circuit? Okay, so there's a resistance here which is fixed, and the resistance of the thermostat, as you can see from the graph, as temperature goes up, resistance drops. So key thing to remember, what formulas can I use? I can use V equals IR only. So that's your go-to formula, whether you use it here or whether you use it there or whether you use it as a whole. So for example, if you got 12 volts, these two, because it's in series, R total is R1 plus R2. So 12 volts, you can now make that as one total resistor to work out the current. So I here will be 12 over RT. Okay, so you could do it that way. All right, so but I'll show you another way anyway. All right, so what we got here, cooling system inside the vending machine turns on when the temperature of the thermos is 20 degrees. So I'm going to find 20 degrees. Clearly they mentioned it. I've got to do something with it. Determine the PD, so they want me to work out voltage across the thermistor when the temperature is 20. So in order to work out the voltage, V equals IR, I need the resistance. Okay, the resistance will help me work out the total resistance. The total resistance will help me work out the current, and the current, in effect, because the current here is the same as the current there, the current will help me work out the voltage here. So if you go up and you go across, so first of all, that's 80 ohms. So there's my first mark. Okay, so there's your first mark. Now, there's two ways to do this. So I'm going to show you both. So use the physics equation sheet. Like I said, the only formula, your go-to formula for circuits, V equals IR. Okay, so most of the formulas you need to use for paper one are all these plus these two at the top. Okay, these are all chapter 6. Okay, but we'll come to that later. These are all paper 2. In fact, is there anything, let me just check, that you probably use on paper 1? Maybe not. Okay, maybe this one, but I'll come to this one in a minute. You won't use it, but you will have to reference it, but we'll come to that. So what do we know? We know the thermistor. If I was to redraw this, obviously I could draw it here, but I'm just going to redraw it. So now you've got 400 and you've got 80. Okay, and that's 12 volts. So what's the total resistance? So I'm going to use this formula here. I is equal to 12 over 480. Okay, so if you did 12 over 480, which is 0.025 amps. Now, what do I know? The current in this one is 0.25 amps. The current in this one is 0.25 amps. Why? Current stays the same. The current here is 0.25, the current here is 0.25, the current here is 0.25. Okay, so we've got some marks already. Now to work out for this one, V equals IR. Okay, so the voltage for this, so the current is 0.025 times R, which in this case is 80. So you put all that in, so quarter, so that's about 2 volts. Okay, if that is 2 volts, that is 10 volts, because these two added together must equal 12. Okay, now this just brings us on to the lateral way of thinking. So I've told you this formula here, and I've just told you, so V equals IR, and I is the same, or it's constant. So that means V is proportional to R. So that means the bigger the resistor, the bigger the voltage you take, or the bigger the potential difference. So who's bigger? Well, 400 is bigger, so it's going to take a bigger share of 12. Okay, well, how much? It depends on the proportion. Well, we know it's bigger because if this is 2 volts, that's going to be 10 volts. But let's prove it. So what do? You work out the total resistance is 480. Then you think, well, what is 80 of 480? So 80 as a measure of the total is a 6. So what that means, it takes a 6 of the voltage. Okay, so you times that by the voltage, which, well, 12 divided by 6 is 2 volts. Do you see how I did that? So that's, look how much writing I've done there. It's not much at all. And that will get me 5 marks because it says just determine. All right, it says use the physics equation sheet. I've essentially used the proportion idea. Okay, this will get you 5 marks. This will get you 5 marks. Okay. Yeah, so this question, now what could they ask you now? What ifs? So let's go through. So the temperature is 20. They could ask you one or two things. They can ask you, what happens if you get colder? What would happen? Or they could ask you, what happens if you get hotter? Right, so it's just knock-on effect. So if you go colder, so let's word this out. The resistance of the thermistor goes up. So if the resistance of the thermistor goes up, what happens to the total resistance? Total resistance goes up. If the total resistance goes up for the same voltage, the current goes down. Okay, knock-on effect, knock-on effect, knock-on effect. Now look at what we wrote here, V is proportional to R. If the resistance of the thermistor goes up, the voltage of the thermistor goes up. Now, if the voltage of the thermistor goes up, this voltage plus that one must equal 12. So if this one goes up, this one must go down. So the voltage of the 400 goes down. That's your what ifs. That's what they could ask you. Okay. Now look at this one. What happens if you go hotter? So it's the opposite argument, isn't it? Now we could actually do the calculations. Well, you could actually just change the numbers here. Instead of 80, just choose, go to 15, go to 200, etc., etc. All right. Now, if you go hotter, the resistance of the thermistor goes down. So the total resistance, because you add them, goes down. If the resistance goes down, remember what we said, resistance is inversely proportional to current, then the total current goes up. Or just look here. If the total resistance, if you divide by a smaller number, you get a bigger current. But then look at if the resistance of the thermistor goes down, the voltage of the thermistor goes down, and therefore the voltage of this must go up because these two added together must equal 12. Okay, this goes up. Okay, so that's your what ifs. That's as hard as electricity gets. Okay, the only thing that makes electricity as hard is what I told you earlier about the required practical, which I can't find anymore, is this one here. What's the effect of turning a series circuit to parallel? Turning a series circuit to parallel increases the current. Okay, because the voltage across these are the same. All right, so just be mindful of that. Again, this could be a thermistor. They could equally have an LDR. Now, if it was an LDR, the circuit symbol is a light dependent resistor. So arrows coming for the light. Sometimes you see the circle around it, you can draw that. So resistance against brightness. Now, how would this change? How would this whole physics change if they had an LDR? It's the same graph. Okay, so instead of it going colder, you'd say darker. Instead of it going hotter, you say brighter. Okay, and that's it. Same explanation, same physics, same maths. So moving on to the next question. So this, in a ride at the theme park, so this looks like your energy question. So this is your chapter 1. What could they possibly ask you? What's the most demanding thing for chapter 1 is conservation of energy, not questions as in like the theory, but conservation of energy calculations. Okay, classic ones that you normally see, which I'm predicting this is not going to come up, I don't think, again. Okay, classic questions, ball drops off a building, work out the velocity when it hits the ground. So at the top of the building, you know the GPE, so you can work out the GPE, which is mgh. GP at the top must equal K at the bottom, so you know the kinetic energy at the bottom because you worked out the GP at the top, and then they make that equal to half mv squared. Or vice versa, you kick something up in the air, you know the kinetic energy before, you could work out the GP after because they'll be the same, and then work out the height from that, okay? And then the usual what ifs, the last bit's a classic what if. So we'll talk about that in a minute in relation to all the questions. So let's look at this question. Ride at a theme park, person is strapped into a pod that is attached to two stretched bungee cords. The bungee cord behaves like a spring. So springs, now you could think two things. F equals KE, Hooke's law, but do not think that, because that's chapter 8 and that is paper 2. So the only thing you should be thinking here is elastic potential energy, and if you look at your formula sheet, elastic potential energy is a half KE squared. Okay, so if they give me a K somewhere and I have to work out an extension, either directly, they give me the extension, or I have to work it indirectly, like what's the new length, what's the original length, then I'm going to use EP equals half KE squared. So if you look here, before release, stretched, you have huge amounts of EPE, initial. So initial EPE. After, what happens to all the EPE? Well, it's not stretched anymore. That now turns into final GPE. In the middle somewhere, it may have been kinetic energy, but maybe that's not what they're asking. Well, clearly not from here. So which energy still increases as the bungees are stretched? So that's elastic, so elastic potential energy. Okay, so this is as hard as they get when you have to, conservation of energy, make one equal to the other. Okay, so when the pod is released, the pod accelerates upwards. Before the pod is released, the extension, so there's your E. Okay, the spring of constant of each. Okay, each. Now the reason why it's underlined, because there's two bungees. So there's 2 times the EPE. Okay, so there's your K. Extensions in the correct units, newtons per meter, that's fine, that's what we want. There's your mass in kilograms, that's great. Why have they given us G? Look at your formula sheet, where do you use G? Half mv squared, mgh, that's the only time you use it on paper 1. Okay, the only other time you use it, weight equals mg, which is paper 2. And I think you use it again, rho gh, I can't remember where it's gone, there you go, rho gh, pressure in water, but we're not interested in that at the moment. So calculate the maximum height. So they're asking for h, question mark. 6 marks, again, use the physics equation sheet. So what do we know? I've sort of already wrote it, haven't I? So the initial EPE is a half KE squared times 2 because of this. So I can work that out, so that's a half times K, which is 735 times 8 squared. So just make sure you do that, and then just times all of that by 2. Okay, so just put all your numbers in. This will give me, just get a calculator, so that is 20, so I've got to times it by 2, so it's 23,520 joules times 2. So that is equal to 47,040 joules. Okay, so that's my initial EPE. That now is equal to my MGH, the GPE afterwards. So I know the mass, I know G, so 47, so I'm just going to write every line of the working out, you don't have to. Okay, is equal to 240 times 9.8. Always use 9.8. Do not use 10. Okay, if you want to use 9.81 because you've looked at some A-level textbooks, then I'm sure I'm pretty sure they're okay with that. So H, so 47,040. So I'm going to take these two over to the side because they're multiplying, you divide. So over 240 times 9.8. So do that first, do the bottom first, press equals, then do 47,040 over that. Okay, let me just do that for you actually. So I would do 240 times 9.8 equals, and then you just do 47,040 divided by answer equals. Okay, so that will stop any calculator problems or issues with the calculator that you have. 20 meters. Okay, again, if you want to put that in there, that's fine. Now, these sort of conservation of energy questions only work in a closed system. Okay, and when you do the calculations, it is a closed system. Then there'll be the what ifs, and the what ifs will be, well, you're actually not going to reach that height. So why is it you don't reach that height? Clearly that means all of the initial EPE didn't get converted to GPE. Okay, so where did it go? Well, what is the most wasted or useless form of energy that we sort of experience? Thermal. So what causes thermal energy? Well, this is going up in the air. So you could argue there's two things here. You could say the air resistance, air friction from the air particles causes some of the GPE to be converted to thermal, or you could say the rubber bands themselves. So if you ever stretched an elastic band, you notice that, if you stretch it 100 times, you put it on your cheek, it's actually quite warm. Okay, so not all the kinetic energy, so not all EPE, elastic potential energy, gets converted to GPE. Okay, so some, because it says explain, that's just a statement, this is the explanation. Some EPE gets converted to thermal because of air resistance, and that's usually always the answer. So classic questions, things rolling down the hills, GP at the top, K at the bottom. Why did you can work at the velocity at the bottom, you just do mgh at the top equals half mv squared, and then the speed that you calculated is actually greater than the real value. Why? Or why did it not reach that theoretical maximum speed? Basically, always this. Not all of the original energy got converted to the final because of some work done against friction. Okay, so just be mindful of those, and therefore there's less kinetic energy or final energy at the bottom. Sort of things you got to look out for. Chapter 1, other formulas. So if you look here, if I just get the sheet, so half mv squared to half ke squared. Now, from what I remember, that was the question on the 2023 paper. Okay, so they've sort of, I think they've exhausted elastic potential energy into kinetic or GPE. So whether there'll be another one of those, very unlikely. I think there was a question on the double award a while ago, the trilogy, sorry, where they talked about the elastic energy inside a kangaroo's Achilles converts to GPE when it's, so they actually gave you the spring constant of the tendon in a kangaroo. I think they've sort of exhausted that. I think they'll probably go back to traditional GPE equals to KE, things going down a slide, okay, roller coaster rides and things like that. So just make sure the energy before equals energy after for your calculations. Use your formula sheet, you obviously got that now. And then last bit of the question, doesn't always reach that theoretical value that you calculated, in this case the theoretical height, because some of the energy is dissipated into because of thermal energy, and explain why, because of friction, air resistance, drag, and so on and so on. Okay, so that's the sort of thing you got to look out for on chapter 1 question. Okay, so moving on, question 7. So this is your required practical. So again, like I said, if I bring this out again, so 2024, we talked about resistance against length. We talked about density now. We said it'd come up. It's obviously come up, and it came up 2 years ago. Whether it's going to come up again, because I think they've pretty much done that to death, really. So we need to look somewhere else. Thermal insulation, specific capacity, maybe IV graphs, but then again that came up 2023. So whether they're going to do that as a method, I'm thinking these two will be your methods, your 6 markers, and so on. This one will be nice because you get nice cooling curves. So it might ask you to analyze here, like here. But this one especially, be a nice plan. Whether they ask you to do results and graphs, but there's certainly variables anyway. Okay, so just again go back and look at those. So let's look at this one then. So what we got a measuring cylinder containing some water with a student used to measure the volume of a metal ring. Metal ring, so that's an irregular solid. So because it's an irregular solid, you use a displacement method. Okay, so whether you use Eureka cans, or in this case, they just basically put it in, the volume of the water goes up, or the level goes up, difference in the levels is the volume of the ring. Okay, it's a simple displacement method, or Archimedes sort of idea. Okay, so if you read that, that's exactly 5. Obviously, when you read it, read at eye level to avoid parallax. Parallax is human error. Human error, never say human error. Human error is a form of, here you go. When measuring the volume, the student's eye was in line with the level of water. So you should always look at eye level. Which type of error would have been caused if the student's eye was not in line? So this is parallax. Anything to do with the human or you being bad at doing practicals, that's random. Systematic and zero error, they're instruments. Okay, how do you eliminate these? Repeats, averages, identify anomalies. Okay, that's how you deal with random errors. How do you deal with systematic errors? Well, zero error. Think of a mass balance, or think of your weighing scales when you check your mass, or check your weight, sorry, or check your mass actually. You make sure it's on zero before you stand on there, because otherwise, let's say it read 0.5 kilograms before you stood on there and it's now 80.5 kilograms. Clearly you're not 80.5, you're 80. You have to subtract the 0.5. Okay, other systematic errors, ammeters, the voltmeters, anything, any instruments you read off, the voltmeters, the power supplies, etc. Random errors, you timing using a stopwatch, you measuring using a ruler, obviously reading off values, which are a bit more difficult, especially if there's not a digital display. If it's a digital display, then it probably won't be a random error. So the student tied a piece of thick string around the metal ring and lowered the ring into the water. Now, I don't know why they want to do that, because metal will sink anyway. Okay, so maybe just to pull it out, but okay. So I suggest one reason why the student should have used thin string. If you use thick string, then that would have a larger volume, which would affect volume reading of the ring. So you want whatever you're using to have negligible volume reading of ring. Okay, if it was something that floated, what do? You got a couple of choices. You can either use your finger, okay, just make sure you don't press your finger in, or just use a thin pin. Okay, again, or the other thing you can do, you can tie it to something that's more dense than water and the volume that you know, so you'll subtract it from the volume of the floating object. Okay, so the volume of the water is 5, volume of the water in the ring is 5.4. So if you look here, the resolution of this, the amount of detail you can read to is the smallest one, that's 1, so 0.2 centimeters cubed. So you can only read to 1 decimal place. Okay, 5.4, so the volume of the ring, so you work out the difference in the levels, 0.4. The true volume is 0.44. Even without the using the string, the measure, so it could not give an accurate value. We just pretty much answered that. Okay, the cylinder, the measuring cylinder can only measure to 1 decimal place, okay, or the resolution is not high enough. Okay, the student used the balance to measure the mass of the ring. Measure the mass of the ring before you put it in the water, because otherwise the water will increase the mass of the ring. After the ring was removed from the balance, the reading of the balance was 0.2. So there's your zero error. Okay, you should have zeroed it before you used it. So if you ever have to write a plan for this one, and again, I don't expect you to see this come up, then and make sure the balance is 0. How could the student use the reading from the balance to determine the correct mass? So basically subtract 0.02 grams from balance reading. I'm not sure why you need 4 lines here. Just be mindful, as you see, you're probably thinking, I don't like writing. It's not that. I just don't need to. You only need to answer the question. You don't need to write reams and reams of stuff. It's not an English exam, okay? They're not marking your spelling and punctuation, or they stopped doing that a while ago. Even if you can't spell the word reading, so long as it looks okay, that you'll be good. Okay, they might laugh at you, but they'll be good. But you don't know they laughed at you. All right. Okay, so the student determined that the density of the ring was that. So kilograms, meters cubed. So those are what we expect the units to be in. The volume of the ring was this. Now you got a problem we want it in centimeter cubed. Okay, calculate the mass of the ring, give your answer in kilograms. So kilograms, meters cubed. So we need this in meters cubed. Now, what do we know? This is where it gets a bit tricky. So what do we know? A centimeter, how do you go from centimeter to meters? You divide by 100. Okay, most of you know that. Or if you do it in standard form, so if I said to you 2 centimeters, that's the same as 2 times 10 to the minus 2 meters, because that's 0.0212. Does that make sense? Okay, so therefore, this is now cubed though. So it's minus 2 cubed. Okay, so that now becomes, if that, let's say for example that was the volume, that now becomes 2 times 10 to the minus 6, 2 times 3, okay, meters cubed. All right, so now that's really tough. Okay, so this one will now become 0.44. So remember that conversion, centimeter cubed to meter cube is minus 6 times 10 to the minus 6 meters cubed. Now normally when you do standard form, we like a non-zero value before the decimal. We do. It's not going to affect your calculation though. So if you're worried, oh, is that become 4.4 times 10 to the minus 5 or 4.4 times 10 to the minus 7? Who cares? You're going to put it in the calculator anyway. And it says calculate, so just give me the final answer. Okay, so use the physics equation sheet. So the one we're using here is density is mass over volume. Okay, so density is mass over volume. I'm going to put the numbers in first. So the density is 21,500 is equal to the mass we're trying to work out over. I'm going to leave it like this, but if you really wanted to know, if you're going to shift it once more, you're shifting it to make it smaller. So that's 4.4 times 10 to the minus 7 meters cubed. Okay, just for the maths weirdos who like everything perfect. So 4.4 times 10, caved in already. 4 times 10 to the minus 7. So how do you work out the mass? You got, because it's dividing, when you take it to the other side, you got to multiply. So 21,500 times 4.4 times 10 to the minus 7. Okay, so if I put that in, so I get 0.00946 kilograms. Okay, which is fine. They didn't say give it in standard form or anything, but in standard form, just shift it 1, 2, 3. So it's 9.4 times 10 to the minus 3 kilograms. Okay, or 9.5, sorry. But that's fine. That's fine as it is. All right, so that should get you the marks. All right, so moving on to the next question. So this straight away, pressure, volume. So this is chapter 6, pressure and volume, PV. So what for? If you look at the formula sheet, it's this one here. PV equals a constant. Right. So PV equals a constant. However, or this is otherwise known as Boyle's law. Okay. So, Boyle's law states that pressure is inversely proportional to volume. However, this question does not look like it's going to use P and V as a calculation, but I will go through it because, or I'll go through an example just so you can see. So let's have a look at the question. This seems a bit more descriptive. And if I look, oh, there's a calculation, but specific capacity. So that is clearly not PV. So we'll go through a PV calculation in a minute. In fact, I'll try and use this one. So when the plunger was pushed slowly into the syringe, the pressure in the syringe increased. So it is actually the theory, but not the calculation. Explain why the pressure increased. Okay, temperature remains constant. So this only works at constant temperature. Okay, so that's really important to know. So when the plunger was pushed slowly into the syringe, so what does that mean? That means V decreased. Okay, so if V decreases, so basically what we're trying to say, pressure is inversely proportional to volume. If V goes down, P goes up. All right, that's the mathematical reason or explanation. But we obviously got to be able to give a physics explanation, i.e. tell me in terms of particles. Okay, why did the pressure increase? Okay, so clearly, if the volume decreases, the space inside decreases. This is just stating the obvious, it's not actually the answer yet. This is what you've got to be thinking. Okay, so what does that now mean? If you've got particles in here, gas particles moving with continuous random motion, okay, and moving at large speeds and a range of speeds, they're going to be knocking on the sides of the syringe. So if you make the space smaller, so there's more collisions per second. Really important to make a reference to the rate of collisions or frequency of collisions or collisions per second. Okay, if there's more collisions per second, there's a larger force because they're hitting the walls. Okay, or there's a cumulative larger force per second, and this means greater pressure. And you're probably thinking, I've seen a formula before with pressure. Yes, but it's on the wrong paper. But here, I'm now going to use that one. Greater pressure. I'm going to use it in my explanation because pressure is force over area, and this has gone up, hasn't it? The force has gone up. In fact, the force has gone up and the area has gone down. So therefore, greater pressure. All right. So now, why is it important that temperature remains constant? If temperature, let's put this down. So if temperature goes up, particles move faster. So the kinetic energy of particles goes up. So that means more collisions per second because they're more likely to bounce off one more than the other in the same amount of time. And they hit it with a larger force. So there's an even larger force, even larger pressure. Okay, so now the volume is not the variable that's affecting pressure. Now the temperature is. So we're going to keep the temperature constant in order to test the relation between these two. Okay, now we haven't seen a P1V1 question here. So what could they possibly ask? So let's look at these numbers here. So let's say this one here, P1 is 1 ATM from just reading there. And V1, if I read that at eye level, of course, 2246, so 26 centimeters cubed. So let's call that V1. Let's say, for example, you squashed it, okay, and it went to there. All right, so that's where it went to. So what is it now at? Let's say V2 is 15. Okay, so the question centimeters cubed. So what question is, what's P2? What's the new pressure? Right, now go back to your formula. PV equals a constant. We don't use it like that. What do? We turn this into P1V1 equals P2V2. So I suggest you memorize that. Now, first of all, before you use it, what are you expecting? If the volume goes down, you're expecting the pressure to go up. Okay, so the volume goes down, the pressure goes up. So I'm expecting P2 to be bigger than 1 ATM. ATM means atmospheric pressure. Okay, so let's put the numbers in then. So P1 is 1 times 26. Now, do I convert these to meters cubed? Because I just told you about that. Well, no, because they're both centimeters cubed, so I can leave it as it is. Okay, so that times V1, I've done that, haven't I? Equals P2 is what I'm trying to work out, times 15. Okay, so what do? Take the 15 over. So if I just do that quickly, 1 times 26, 26, of course, 26 divided by 15. Okay, so that gives me a pressure. So P2 is equal to 1.73 ATM, which makes sense, okay? Because if you decrease the volume, you increase the pressure. Expect a P1V1, P2V2 calculation because it hasn't come up here. All right, so a fire piston is a special type of syringe that can be used to start fires. Okay, when the plunger is pushed quickly downwards and compresses the air, when the air is compressed quickly, the temperature of the air increases. Now, this is really important because this is the last specification point on this. When you do work, when work is done, and you need to remember this, when work is done on a gas, so the best way to think of this, think of the football pump, okay? When you keep plunging it in and out, you put your hand on the pump itself, you'll notice it's got hot. So when work is done on a gas, temperature increases and internal energy increases. Now, if you remember, what is internal energy? it's equal to the kinetic energy plus the potential energy. We haven't changed the state, we've changed the kinetic energy. We've made them move faster. Okay, so by doing work on the plunger, you're making the particles move faster. Okay, expect what hasn't come up yet is your classic, if you remember, temperature against time of this one here. Okay, know when to use equals mc delta theta on the diagonals, oops, sorry, and know when to use equals ml, which is the horizontals of the change of states. Okay, so how does an increase in temperature affect the particles? If you increase the temperature, they move faster. Okay, the increased kinetic energy, so therefore the mean kinetic energy of the particles increases. How do you increase the potential energy? You make them further apart, i.e. you break bonds or you change the state. So when you go from solid to liquid, there's a small change in internal potential energy, but when you go from liquid to gas, because you're separating all the particles, you're breaking bonds, potential energy increases rapidly. So just be mindful of that. Okay, so then moving on. Now this sort of is a bit cheeky. I thought it was a chapter 6 question. Now it turns out to be a chapter 2 question, because chapter 2 in the textbook was specific heat capacities. So what do we know? We've got the energy, and that's in the correct units. We've got the mass in kilograms, so that's good. Specific capacity, kilojoules. Okay, so we've got to convert that to joules. So that's 1010, if you times by 1,000, joules per kilogram degrees Celsius. So there's your first mark, because that's, why else would it be for? And what are they asking for? They're asking for the temperature change. They're just asking for delta theta. Okay, so use physics equation sheet. So if you look on your sheet, E equals mc delta theta, so make sure you use that. So E equals mc delta theta. You don't get a mark for that, so put your numbers in for your first mark. So 0.0130 is equal to the mass, 2.6 times 10 to the minus 8 times 1010 times delta theta. So then take these two over to your side to get delta theta on its own. So delta theta is 0.130 over 2.6 times 10 to the minus 8 times 1010. So put that in. Now, if you didn't convert the specific capacity, you'd only lose 1 mark here. Okay, because it's transferred error. Okay, so the rest of your physics is fine. All right, so that gives me 495. So I'm giving it to 3 significant figures. Why? 3 significant figures, 3 significant figures, 3 significant figures. Okay, so don't give it to less significant figures. Okay. Okay, question 9. Teacher investigated radiation emitted by 2 different radioactive sources, A and B. Figure 14 shows a radiation detector, a Geiger-Müller tube, if you want to call it that, positioned near one of the radioactive sources. Okay, so radiation coming from there, hitting there, and this counts the number of counts per second, or the activity, which we measure in, well, in this case it's counts per second, but we normally call it becquerels. Okay, so if you increase the distance, clearly the count rate is going to drop. Okay, so teacher measured the count rate at different distances. All right, so if you look at A and B, they're both dropping. That you expect that. A has dropped dramatically, but it's never reached 0. Why? This here must be the background radiation. So background radiation looks like it's approximately, well, half a box. Each box is 50, so it's about 25 counts per second. Okay, so what causes background radiation? Rocks, building materials, radon gas that was trapped in the rocks that was excavated, cosmic rays from space, your food. Those are the natural sources. And then the artificial nuclear weapons, nuclear power stations, weapon testing, and hospitals. Okay, so you should never really reach 0, but when you do activity calculations, you should subtract the background from it, if they ask. Now, explain how figure 15 shows that A only emits alpha. What do you know about alpha? Alpha, helium nucleus, 2 protons, 2 neutrons, charge of +2, really heavy, really slow, highly ionizing. Because it's highly ionizing, it bumps into lots of particles and therefore loses its energy as it's ionizing those particles, therefore loses energy very quickly, therefore has a small range, has a range of a few centimeters in air. Okay, so there's your answer to that. So if you think about it, I've pretty much, just by recalling the knowledge, I've answered it. But I've got to use figure 15, so let's use it. So it drops to background level after 3 centimeters. So it drops to background level after 3 centimeters. So the range is a few centimeters. Okay, so this must be alpha radiation because it has a short range. Okay, so sort of going around in circles answering this, trying to work out what the 3 marks are. So figure 15 cannot be determined to determine if source B emits beta or gamma. Okay, so what can you do? What's the difference? Well, we know beta travels several meters. We know gamma travels several kilometers. Okay, because of their ionizing properties and so on, and their speeds, etc. So what can we do? Well, what do we know? We know they're stopped by different things. So explain how an absorbing material. So what stops alpha? Thin paper or few sheets of paper or skin. What stops beta? Thin sheets of metal. What stops gamma? Thick concrete or lead. All right. So if you place, so to prove it's not beta or it is beta, place a thin sheet of metal here. So place a thin sheet of metal, and in this case it would be aluminium. And if it drops to background level, then it must be beta. Okay, if it doesn't, then if it stays above background radiation level, then it must be gamma. Now, it will drop a bit even if it's gamma, but it won't drop significantly. Okay, so gamma will, the thin sheet of metal will block it a little bit. There's no point using concrete or lead, because concrete or lead will cause both beta and gamma to drop to background level, so you wouldn't know which one it is. Okay, so just be mindful of that. So again, all they're doing, they're just looking at the properties, uses, not the properties, penetrating, ionizing pairs and so on. So suggest one precaution the teacher would have taken to reduce it. So just use your common sense. Okay, use tongs or forceps. Okay, don't handle it yourself, otherwise you may get contaminated. Okay, use tongs, forceps. Limit your exposure time. I've given 2, I don't have to. Other things you could have said was increase the distance between you and it. Make sure it's not pointing towards you. As weird as it sounds, you can wear a lead apron, or you could wear a radiation suit or a bunny suit, as they call them. Keep it inside a lead box and stuff like that. Now, suggest one safety precaution the teacher should use to avoid being contaminated. So contaminated means it's got on you or inside you. Okay, so clearly you don't want it on your skin, your hands, you don't want it on your whatever. So wear gloves. In fact, you could have said this here as well, actually, in the previous question. Wear gloves. You could have said things like wear your lab coat, wear lead apron, don't handle it yourself, etc. So contamination means it's got on you or inside you. Irradiation means you've just been exposed to it in the same room or the same area. Okay, don't worry too much about being exposed, because you're being exposed to background radiation right now. It's not hurting you. But if you got contaminated by alpha, beta, or gamma, you're going to be in a spot of bother. Okay, so let's look at the next question. Right, so this looks like your half-life graph calculation, but it's not. So like I said, there's been no half-life calculation, so expect those. Figure 16 shows how the number of atoms of a radioactive element in a sample varied with time. Activity is the rate. Rate means divide by time. Okay, of an unstable nuclide. Determine the activity of the radioactive sample at 300. So what you do, this one's, so you've basically got to do the sample, the number, divided by time. So how do you do that divided by time? Well, if this is a straight line, you do the gradient. Because it's a curve, you've got to do the tangent. So I'm going to try and draw a tangent with this. It's not ideal. So it should be, in fact, it's probably better actually. So there's my tangent. Okay, that'll do. Try and draw it bigger if you can. Actually, I'm happy with that. So there, from there, and let's go to here. Sorry, there. So that is 250. That is 400. That is 2 times 10 to the 23, and that is 3.1. Okay, so this is 1.1 times 10 to the 23, and this is 150 seconds. So if you then did 1.1 times 10 to the 23 over 150, so punch it all in. So 1.1 to the xp23 divided by 150, so that gives me 7.33 times 10 to the 20, and the units of activity counts per second, or what we call becquerel. Now this is a really unusual graph analysis. Normally they just ask you to work out the half-life. Okay, so there hasn't been a half-life question yet. Okay, so something to expect. Okay, so last question, live wire. So this is chapter 5 again, is it mains electricity. So live wire in a 3-core cable is connected to a fuse inside a plug. Fuse contains a wire is designed to melt when the current gets too great. So we talked about this, if you remember, sort of preempted. If I can find it, here you go. Nope, not here. Here you go. So we talked about it here. Right, okay, so fuse contains a wire that is designed to melt when the current gets too great. So what colour is the insulation covering the live wire? So we said the live wire was brown. What does the fuse look like? So we've already drawn that. It's got the wire in the middle. So the fuse wire melts when there is a charge, Q, in this time of 400. Now remember what we said? Lowercase m is milli. Alright, so 4 milli times 10 to the minus 3, so 400 times 10 to the minus 3 seconds. Okay, again, 4 marks for quite a straightforward Q equals IT question. So what formula are we using? What do you know with Q, I and T? So it's this one here. So we've actually used quite a lot of the formulas here in this paper. So the only ones we haven't used is power, work done over time. So maybe something like that on the energy questions. Don't forget the work done on power. It could be this energy, it could be this energy, it could be this energy. In fact, it could be this energy. Okay, so that might be something to expect for specific capacity, how they do the calculations with that. So let's just do this one anyway. So we've got Q equals IT. Okay, so I'm going to put the numbers in first. So 2 is equal to I times 400 times 10 to the minus 3. Okay, so we can work out I, so it's just simply 2 over 400 times 10 to the minus 3. And again, I've not turned this into a decimal because I'm just going to put it straight into the calculator just to show you. So it's 2 divided by 400 to the xp minus 3. There's no need. Just complicating it for yourself. So we've got 5 amps. Alright, so when the fuse wire is at its melting point, the additional energy needed to melt the wire is this. So that's your energy. Specific latent heat of a fuse wire, so that's your L, but we've got a problem. It shouldn't be in kilojoules, it should be in joules. So that's 60,000 joules per kilogram. Okay, calculate the mass of the wire. Okay, so again, question mark. All right, so E equals ml. which is the formula here. So we pretty much used everything except PV equals a constant, and except pair equals energy over time. So pair equals work done over time. So just be mindful, that's something they could ask you to use. Everything else, I think we've used. In fact, we haven't used half mv squared. So maybe that could be your energy conversion, as we talked about for chapter 1 question. So, and again, we've done plenty of those. So just revisit those. So 1.02 is equal to m times 60,000. Okay, so we can work out m, take the 60 over because it's multiply and divide. So 1.02 over 60,000. Okay, and that will give you, so 1.7 times 10 to the minus 5 kilograms. Okay, so that's fine, that's nice and easy. Just seems to be doing formulas for the sake of it. So let's look at the last bit. The calculation 10.4 assumes there's no energy transfer to the surrounding. So this was your classic, when you did E equals ml and E equals mc delta theta experiments, they'd always ask you at the end, the experimental value for C that you got was too high, or the experimental value for L you got was too high. Why? Because what you forgot to do was insulate around it. And because you didn't insulate, energy was dissipated to the surroundings. Right, so they're telling you the energy dissipated to the surroundings. So let's say, for example, so how would the time taken for the wire to melt be affected if some energy was transferred to the surroundings? So let's say, for example, the wire needed 100 joules to melt, but you supplied 100 and 20 joules of it disappeared into the surroundings. You've only given it 80. Will it melt? No. You need to now give it another 20 joules. So that's going to take a bit more time. So therefore, time taken would increase because more energy is needed to melt the fuse. Now, this is like I said, in terms of what we've seen so far for it sort of predicts. So it's not really predicts, but sort of questions that have not come up. Your classic E equals mc delta theta, or even E equals ml. Experimentally, how would you work out E here? So if you go back to your formula, the energy equals power times time, or power equals energy over time. Energy equals PT. So therefore, PT here is equal to mc delta theta, or the energy supplied here, practically PT equals ml. Now, if it was electrical power, then you could argue it's actually, because power equals IV, then IVT equals mc delta theta. Then that would inform the sort of experiment. The reason why I bring that up is because that could be what's coming up, because that hasn't come up yet, has it? So think of, I'm not sort of putting all my, I'm not banking my house on specific capacity, but it's sort of calculations that haven't come up, that could come up. And again here, IVT is equal to ml. That's if you did it experimentally. So if you think experimentally, C is equal to IVT over m delta theta. And we did this as an experiment. I is the ammeter, V is the voltmeter, T is the time, m delta theta you should know. The other way to do it, if they give you a graph of, what would it be? Change in temperature, temperature against time. Okay, sorry, instead of temperature, let's put or delta theta, right? The graph looks like this. Okay, so you've got this bit here where you switch the power on and nothing's happening. Why? Because the heater is still warming up. All right, so what should you have done? You should have preheated the heater before you put it in. Now, how do you work out C from this? So you've got this is supposed to be linear, by the way. You've got this linear bit, which is delta theta over time. Now look at your formula. Let's go back to this one. So PT equals mc delta theta. How could I rearrange this formula to get delta theta over time? So delta theta, bring the time to this side, bring the mc to the other side. So you've got delta theta over T is equal to P over MC, and maybe P is equal to IV, all right, but let's assume it's not. So therefore, the gradient, this is the gradients, isn't it? This is the gradient, is equal to P over MC. So you can work out C is equal to P, the power, over M times the gradient. So just be mindful, that's one way of them asking how to work it out. If they wanted, if I just go back to here, if they make you try to work it out from the graph, okay, obviously you have to think about what else you could do there. So that is basically a 2024 walkthrough, and sort of give you a sort of inkling as to what to expect on 2025. If you enjoyed this, then